This video, we're going to do another UNISIM tutorial. So in this one, we're going to solve a very short problem that involves mixing 1 kilogram of steam at 200 C with 1 kilogram of steam at 300 C. And the whole process is going to be isobaric at 1 bar, and we want to calculate the final temperature and the entropy generated by this process. So right off the bat, I picked very easy numbers. So mixing equal amounts of steam at 200 and 300 C at the same pressure. Kind of intuitively, we know that the answer should be around 250 C, but perhaps not exactly 250 C because of the way the energy balance works out. In the energy balance, you have to make sure that the enthalpy is kind of averaged, not the temperatures. So because H is a nonlinear function of T, especially for water and steam at those high temperatures, we may see a little bit of deviation. So in the UNISIM main toolbar, remember we want to go to File, New, and New Case, and that is going to give us a new file. First thing that we have to do is specify which components we have in the fluid package. So in the master component list, I'm going to add a new component list, and we want water. So in the search, no, not watch, water, add pure. And remember to say OK on UNISIM, we could just click the red X and hopefully, yep, it should come back. So I always like to double check by clicking view. Next, we need to define the fluid package. So add, and then remember this is where you define what your model you want to use. So at this point, you can choose a cubic equation of state like Suave, Redlish, Kwong. That's typically a good one if you don't have any other information. What's the other one? Pang Robinson is another good one. But in this example, we just have water. And if you just have water, the best model is going to be the steam tables. So there are two steam table models that are built into UNISIM. One of them is NBS steam, and the other one is ASME steam. They're pretty much equivalent from my understanding. I've only ever used NBS steam. I haven't tried ASME, but I've heard others say that they give exactly the same results. So for this one, I'm just going to choose NBS steam. And you notice that there's no ideal gas or anything like that. So steam tables takes data from the actual steam table. Okay, click OK. And at this point, we are ready to enter the simulation environment. So click this box with enter. And we're back to our familiar green screen. Just one quick useful tip before I begin. If you hit F4, this unit toolbar, you can toggle that on and off. So if it's occupying some space or something, you can always turn it off and get a cleaner look. But we will need to define two streams that are coming together. And importantly, so I said the problem statement, even though I didn't write it, it involves mixing 1 kilogram of steam with 1 other kilogram of steam. So this is not a continuous process. It's a closed not a closed process, but it's a discrete process. And UNISIM doesn't model those well. So you have to convert any problems that you have into a continuous process, into an equivalent continuous process. So when I define the flow rates, I'm just going to arbitrarily choose a time unit, and then I'll just understand that all answers that I get are on that same time unit. So remember, material streams are the blue ones. Energy streams are the red ones. We want to define a material stream, and it will be this light blue color when we haven't defined enough information yet. After we've specified the stream, it should turn a darker blue. So we have to think about how many variables we need to specify. We have the temperature and the pressure of this stream. So I said the first stream was going to be, it's 1 kilogram at 200 C and 1 bar. So remember on the pressure, it wants it in kilopascals, but I can click to whatever pressure I have, and it'll convert it for me to the units of pressure that it needs. So mass flow rate, I'm just going to say it's 1 kilogram, and hours will be my default time unit. So whatever answer I get, I'll just understand that that is, I'll have to divide by that hour back again. All right, now you notice that all these empty cells are still light blue, and my stream is still that light blue color. So by Gibbs phase rule, if we have one component at one phase, technically specifying temperature, pressure, and the flow rate should specify the stream. But remember, in UNISIM, even if you only have one component in your system, you have to specify that is 100% that thing. So you have to specify the composition of your streams. This is a bit silly to me. I don't know why this is not a default, but just something that you have to remember. That mole fraction of water is indeed 100% if it's the only thing in the stream. All right, now we have a dark blue specified arrow. So I want to point something else out to you very quickly. If I pause and go over to the steam tables, so here we are in the steam table, and I have superheated steam. So I want not saturated steam table, I want the superheated vapor table. And I am at 1 bar, which is equal to 0.1 megapascals. And I said 200 degrees C, what is the enthalpy of that stream? 2,875.3 kilojoules per kilogram. Let's see if that same number, so remember that, write this down, 2875.3. All right, so where do we get to what the enthalpy is? All right, so under conditions, it gives you the molar enthalpy. So if you don't want to convert between moles and mass for water, you can get the mass enthalpy under properties. This is the second tab under worksheet. So go down to properties, and here it says mass enthalpy, kilojoules per kilogram, negative 13,049.1. So what's going on here? Why do I get a different answer if I look in the steam table versus on UNISIM? Remember, in the steam table, it was 2875.3. So why is there such a big difference here? The answer is because UNISIM uses a different reference state than the steam tables that are in the Sandler textbook. So that is something that should not affect the final answer, just something that you always have to be aware of, and don't get confused, because remember that it makes no sense to define enthalpy on an absolute basis. There's no such thing as absolute enthalpy. It's always relative to something. So you have to choose an arbitrary reference state, and whatever reference state UNISIM chooses must be a very high energy state because of this negative number. Negative 13,000 kilojoules per kilogram is a very large enthalpy. So again, the answers will work out to be the same. If you do the entire problem in UNISIM, that reference state should cancel. And theoretically, that's a good way to double check if you're doing any calculations by hand. Your final answer should never depend on the reference state that you choose. You should be able to choose whatever reference state you want. And ideally, you choose something that would give you the least amount of work to do. But UNISIM is a computer software, and it doesn't care about how much work. All right, now we need to define another stream. I'm going to click Material Stream and make another one. This is going to be another input to my mixer that I'll eventually have. And notice that it's going to be very similar to the first stream. The only difference is the temperature. So instead of going through and having to specify those things from before, so there's nothing stopping me from doing that, but I want to teach you a quick shortcut. Because it's so similar, I can click this box down here, define from other stream, and tell it to define it from stream 1. And that's going to clone in all the values that I had from stream 1, including this composition. And remember, the blue ones are the ones that I put into UNISIM, and then the black ones are the ones that are calculated from that. So I want to change the temperature to 300 C for this stream. So I have one stream that's 200 and one stream that is 300. Okay, and everything is now specified. Oh, I just noticed that mass flow is the one that I specified. That's weird. Wonder why that is. The numbers are right, so probably not too big of a deal. Anyway, I want to come over to my unit operation toolbar, and you can mouse over some of these. I encourage you to explore what the differences are in some of these things. We want the mixer. So a mixer is going to take two streams and give me an outlet stream. I'm going to right click on my mixer. I'm sorry, double click on the mixer. I have to tell it what inlets I want it to have. And I have two streams at this point. So I have stream 1 and stream 2 that it's going to take as inlets. I have not defined my outlet stream yet, so I'm just going to call that outlet stream is mix. and that's okay. Click the red X, and now I have a whole blue process flow sheet. And if I hover over without clicking what the stream is, I get what the final temperature of this stream is, 250.244 degrees C. So pretty close to my intuition that it should be around 250 C, but not necessarily exactly 250 C. So this slight increase in temperature is again because of the differences in the nonlinearity of H as a function of T, particularly for steam. All right, how do we figure out what the entropy generated by this process is? If I double click on the stream again, see that I have under properties, mass entropy is defined as a property. So my mass entropy of this stream is a certain number, and it's actually the same for any of the streams that I have. So unfortunately, UNISIM doesn't do an exact calculation for you. It doesn't do the entropy balance for you. You have to do the calculation yourself. But there is a handy flow sheet tool in UNISIM, so you don't have to use Excel or you don't have to use a calculator necessarily. So you want to find the spreadsheet. I want to double click that, and I want to go to the spreadsheet tab. And I want to give myself some more room here. So this is going to behave similarly to Excel. It's a little bit more limited than Excel. There's a couple of idiosyncrasies that I'll talk about, but the default is going to be 4 columns and 10 rows. So in Excel, you have an infinite spreadsheet immediately. In UNISIM, not necessarily. So you need to go to parameters, and you can put however many columns or however many rows you want. So I'm just going to go with 7 columns, and that's going to give me some more information. So at this point, pause the video and see if you can work out the algebraic form of what the entropy balance is, get an expression for S dot gen. And I forgot to tell you that it's an adiabatic process, so you can determine that it's adiabatic because in the mixer I didn't specify any energy streams, so that tells you that Q and work are equal to 0. So the Q over T term cancels in the entropy balance. I'm going to assume it's steady state, and actually it's not even steady state, right? Because it's just 1 kilogram mixing with 1 kilogram instead of 1 kilogram per hour. So time derivatives are going to go to 0. Or in the integrated form, that term would cancel as well. So my S generated is going to be equal to the sum of my mass flow rates times my specific enthalpies. So I'm going to need the mass flow rates of all streams. So M1, I'm going to put in cell A2. And specific enthalpy of stream 1. So I'm going to abbreviate here, and I'm just going to say what my abbreviations are. Mass flow rate of stream 2, specific enthalpy of stream 2, mass flow rate of mix, and specific enthalpy of the mixed stream. And then the final cell will be my S generated. All right, this is the cool part about using the spreadsheet in UNISIM. So I can right click on a cell that I want to import my data from. And you see, after you right click, it says import variable. That's what I want. So I want from object 1, which is stream 1, and you'll have all these variables that I can choose from. So I want to scroll all the way down to the M's where I find mass flow. And click OK, and that is going to give me my variable of 1 kilogram per hour. I'm going to continue on in that fashion, so I'm going to import the variable of enthalpy, mass enthalpy from stream 1. Remember, I want mass enthalpy because I have mass flow rate, and I want my units to be consistent. Let's see, mass enthalpy. Click OK. I also like how it gives you the units too. So this is what I mean by units canceling out. So if I multiply kilograms per hour by kilojoules per kilogram, I should get kilojoules per hour, which is going to make sense. That's a rate of enthalpy generation. Okay. Oh, wait a minute. No. I clicked the wrong one, didn't I? This is also why it's useful, because entropy should have degree C in it. Yep, I clicked enthalpy, not entropy. I mix those up more often than I should. But always double check yourself, and then that answer makes a lot more sense. So now kilograms are going to cancel, and I'm going to be left with kilojoules per hour degree C. All right, continue on, importing all my variables. So I'm going to import mass flow rate of stream 2 all the way to the M's, mass flow, object 2, mass entropy. Mixing stream, import variable mix. I shouldn't have named it mix because that's also the name of the unit, but I guess the 100 differentiates it. So I need the mass flow here. Mass flow. Sorry, you have to watch me do this very slowly. Mix mass entropy. Nope, not molar entropy, mass entropy. All right, I've imported my 6 variables. Now my equation for Sgen, as I said, is going to be the sum of the mass flow rates and the enthalpies. So I have to get the sign right too. So double check your sign. It should be final entropy minus initial entropy, should be the entropy generated, right? So just like in Excel, it's equals, but unlike Excel, I can click on another cell to get the cell reference, but it's actually not going to work in a formula form. So I'm pretty sure, right? So I can't just click on E2 times F. That's not going to give me, oh, maybe it does. Maybe it does work. I thought this didn't work. I've tried this before and it has not worked for me in the past. So E2 times F2 minus A2 times B2 minus C2 times D2. Okay, it did work. So it gives me 1.82 times 10 to the negative 2 in terms of enthalpy generated. Now this is good because it tells me that my entropy generated is positive, which that should be the case. I should not have gotten negative entropy from a mixing process. So this tells me, it's a good check to make sure that your sign convention is correct and that you've done things correctly. So it doesn't tell you that it's done it correctly, it just tells you that you haven't done it incorrectly, which is not necessarily the same thing. Okay, one more thing I want to show you, and that is in changing the significant digits that you get in your flow sheets. So I have set it to 6 significant figures. You probably have it set to 4 significant figures. It doesn't really matter. I'm a big believer in fewer significant figures for the most part because it makes things easier to read and contextualize and compare quickly. But sometimes you may want a larger degree of precision. And because the steam tables are so precise, so the steam tables themselves go out to 5 sig figs, and I think UNISIM goes up to 6 sig figs. So if you have that precision, you might as well use it. So under Tools and Preferences, you can go to Variables and Formats. And this is going to tell you how many significant figures you have. So again, the default is 4. So if you double click on Format, it's going to change all the variables. So yeah, again, you probably have it set to 4. I can just go ahead and set that back to 6 if I'd like. And then that's going to give me my greater degree of precision. It's going to make things a little bit trickier to read because it's harder to interpret 6 digits than 4, but it's going to be a little bit more precise. All right, that is the demonstration. Hopefully that helps you with your, you could double check your homework problems with this, by the way. And again, I don't want you to solve problems with UNISIM for the most part. I want you to show your calculations by hand because I think that's the most important part, is understanding what UNISIM is doing. But again, this can be a very useful tool to double check your work.